So, good day, everyone. I am Roselle Ngaloy, and I am a PhD student in the group of Saroj Dash at Chalmers University of Technology. And in this presentation, I'm going to show you our work about room temperature spin valve devices from heterostructures of 2D van der Waals or van der Waals magnet and graphene. So of course, this work is not possible without collaborative work. So for most of these works, I have worked closely with Bing Zhao for transport measurements and device fabrication, while Khadija Ali is a postdoc in our group who does spectroscopic measurements in synchrotron facilities. So for computation, we got support from the group of Biplab Sanyal at Uppsala University, where they do DFT calculations and Monte Carlo simulations. So to start with, the discussions about magnetism at the 2D limit has long started in 1944, when Onsager published his work on 2D Ising magnet that has a long-range order. However, this model is a simplification where the spins can only have up or down orientations. So a more general view would be the 2D Heisenberg magnet. However, in 1966, Mermin and Wagner found out that long-range interaction in these kinds of materials cannot be possible because of with thermal effects, you can have magnons or spin waves, which prevents long-range interaction. But thankfully, in 2017, they have successfully demonstrated monolayer magnetic order in chromium iodide and up to bilayer in chromium germanium telluride. And this has enriched the field of spintronics by giving us materials that has different magnetic properties and antiferromagnets with different electronic properties, such as insulating and metallic. But for the purposes of our studies, we are mostly concerned with iron 5 germanium telluride. Firstly, because it has a high Curie temperature, which could reach a little above room temperature. And the next one is that it has a higher saturation magnetization compared to its predecessor, which is the iron 3 germanium telluride. And lastly, it is metallic, which will enable electrical spin injection and detection for an all-electrical circuit. So F5GT is comprised of telluride layers that sandwiches 5 iron atoms and a germanium atom. But in this structure, iron 1 is a bit peculiar because it is a split site, which means that it could be found in the upside or it could be found in the downside. So calculations from our collaborators found out that in a series of, or in the lattice of FGT, so this FE1 site is actually preferably located up, down, and then up. And this kind of arrangement leads to a square root of 3 supercell that is actually confirmed by STM measurements that we found. And then this square root of 3 by square root of 3 could induce a canted magnetization in the F5GT magnet. So now that we have a van der Waals magnet, we want to put it into a spin valve device. So in a spin valve device, we also wanted a spin transport channel, which graphene is known for. And between graphene and FGT, we should have a good interface such that it supports spin transport or tunneling between the magnet and graphene. And for that, we found out that in our devices, we have about a few kilo ohms of resistance, then we can observe spin injection and detection. So these kinds of devices are actually very sensitive on the interface of FGT. And by applying fields in different directions, such as dx, dy, and bz, we can extract different spin orientations, such as sx, sy, and sz, and this can be correlated to different magnetic moments of the magnet, such as mx, my, and mz. So the first experiment that we did is actually just to see a spin valve. So a spin valve is when you have two magnets and you orient the magnets such that their long axes are parallel, and then you have the graphene here. So by applying a magnetic field along the long axis of these two magnets, we can change the relative orientation of their magnetic moment to be parallel and anti-parallel as we sweep the magnetic field from negative to positive and from positive to negative. And so this signal is actually a typical signal for a spin valve, where the high resistance state is for the anti-parallel state of FGT and cobalt, while the low resistance state is for the parallel state of FGT and cobalt. So both of these were done for FGT injection, which means that we apply the current between FGT and graphene, and for FGT detection, which means that the current is applied using a reference contact cobalt, and the voltage is measured between FGT and graphene. So in these measurements, we have shown the robust spin valve operation in heterostructure of FGT and graphene, and we were able to extract the spin valve or the spin polarization of up to 45%. So because in our device, we oriented the magnetic field along SY and along the y-axis, so we oriented the magnetic field along the y-axis, and the successful observation of a spin valve points to a spin polarization of along Y for the FGT graphene interface. So the next measurement that we did is actually by applying the field along the x-axis. When you apply the field along the x-axis, we process the spins that are injected from the FGT. And with this precession, we can extract how it looks like, how the symmetry looks like, and it corresponds to different spins at the interface. So here we saw an asymmetric X-Hanle data. So an asymmetric X-Hanle data indicates the existence of an out-of-plane magnetic component for FGT. So after that, we did apply a magnetic field out of plane. But this magnetic field out of plane looks like a combination of symmetric and anti-symmetric components. So for asymmetric components, we see SY spins, but for an anti-symmetric components, they are contributed by spins along the X directions. So for the Z-Hanle spin, Z-Hanle measurement, we were able to confirm SX and SY spin components. So now we know that we have SX, SY, and SZ spins, and this indicates that FGT graphene interface has a canted magnetism. A canted magnetism meaning that it's not completely out of plane, but it is at an angle towards the in-plane direction. And that angle is actually confirmed by Monte Carlo simulations, where they found out that the canting angle is 58 degrees. So they were also found out that we have an increased enhanced magnetic moment, like for example, an FE1, like this, and it shows enhanced FM interaction between neighboring iron atoms. So last observation for these devices is that here, if we compare it with a reference cobalt device, which means that both our injector and detector are cobalt, and we compare our FGT cobalt device, at the same bias conditions, we see different polarization of the spin valve signal. This actually points to a negative spin polarization at the interface. So this negative spin polarization was also corroborated by DFT calculations that shows a negative DOS at the Fermi energy, at the Fermi level. The next device that I'm going to show shows how FGT is actually interesting in a way that you can tune its magnetic properties and also its Curie temperature by doping it with cobalt or nickel. But in these studies, we were mostly interested with C15 FGT, which means that 15% of the iron atoms were substituted by cobalt. And from DFT calculations, we found out that cobalt actually wants to substitute at the iron split sites, which I discussed earlier. So these FEU and FED split sites. What it does is that it stabilizes the magnetic anisotropy to in plane. So in comparison to F5GT, now we have an in comparison to F5GT, which has a canted magnetic anisotropy, now we only have a purely in-plane magnetic anisotropy, as confirmed also in bulk samples by SQUID measurements. So similarly, we did spin valve measurements where we used CFGT as an injector and detector together with a cobalt electrode. So similarly, we see a negative spin valve signal, which indicates negative spin polarization of C15FGT. And this was also confirmed by DOS, density of state calculations. So aside from that, when we performed Handle measurements, both applying Z and X magnetic field, we see symmetric contribution, which indicates that these contributions are only for SY spins. So here is another evidence of the strong in-plane magnetic anisotropy of CFGT. So this shows that with doping with cobalt, we can change the magnetic properties of F5GT. So in summary, we have shown the first observation of spin injection and detection by van der Waals magnet at room temperature. And spin polarization could reach up to negative 45%, with FGT having a canted magnetization and in-plane magnetization with C15FGT. So I think our work opens the door for more van der Waals devices at room temperature. Thank you.
Thank you very much for the very nice talk. So are there questions? So I might ask one. It's about the fabrication of such devices. Do you need to exfoliate for obtaining this FGT layer?
Yes, yes, we do exfoliate. So our graphene is actually CVD graphene, and we pattern them into these ribbons or stripes, as we call it. And then this FGT and the CFGT comes actually in bulk crystals, which we exfoliate, and then we transfer on top of graphene to form these heterostructures.
Okay, thank you very much.
Thank you.